a set of 3 tutorials on the subject of functions at the higher level. Now I'm going to break this topic up into 3 parts. This first tutorial will be very introductory. So if you feel comfortable with the concept of a function, you may really want to skip this tutorial and move on to the second and third tutorials. The second tutorial will be taking the introductory concepts that I'll be talking about here and sort of formalizing them into the language we're quite used to with functions, namely sort of f of x and so on. So I'll be talking about sets and functions in a more formal way, and also talking about what are called composite functions. And then in the third and final tutorial on functions, I will be talking about inverse functions. And I'll try to give a number of helpful examples in each of those subsequent tutorials. Now, functions is seen as quite an abstract topic. I think students often feel a bit uncomfortable with it because it's quite abstract. But really, I think the point of this first tutorial in particular is to kind of remind you that actually functions are absolutely a part of our everyday lives. We use them all the time, sometimes without even thinking about it. They're amongst the most intuitive things in mathematics, in fact. And so perhaps the discomfort is more with some of the language that we use when we talk about f of x, for example. So I want to try and just demystify that and get everyone very comfortable and clear and confident with the idea of functions and also just using functions, because they are to be used. They are machines for us to use, particularly when we move into calculus later in the higher maths course, where we will be handling functions as a potter would be handling clay. I've used that metaphor before for a different topic in the National 5. You know, you've got to see some mathematics as just clay for you to get your hands on and to manipulate in a very creative and confident way. So anyway, let's get cracking with this first tutorial, which is very introductory. And we're going to be talking about a character. Let's say the character is a young lady. Let's just give her a name. I'm just going to make up a name, Bethany. And Bethany is very diligent. She is very good at studying, completely unlike me. She's also enjoys kind of the outdoors. So we're going to do one example of functions looking at her study routine, and we're going to do a second example of functions by accompanying Bethany at the weekend when she goes on a hike up a mountain. So this absolutely establishes that she is utterly different to your tutor here, who cannot remember the last time they approached a mountain with an ambition to climb it. So let's have a look. She studies on weekdays, and let me just make a little table here. So let's just say day of the week and how many hours she studies. And also, she's quite smart, you know. She rewards herself with sweets, candy, depending on how many hours that she studies. And so we'll have sweets as another column in this little table I'm going to create here. So Monday, Tuesday, Wednesday, Thursday and Friday. And on Monday she studies for 4 hours, Tuesday 5, Wednesday 7, Thursday 6, and Friday kind of has a half day and just does 3 hours on a Friday. She rewards herself with sweets. She is quite rigorous. She has an algorithm for doing this. So I think her algorithm is that she allows herself to have a number of sweets equal to the number of hours that she studies plus 1. So these are the number of sweets that she has on those different days. Okay. So what I want to do using this little story of Bethany here is to introduce the idea of, first of all, of sets, and then secondly, of mapping an element of one set to an element of another set. So I want to create a set of values which are the days of the week for which she works. So here we are. Here's the set. I'm going to call it capital D for days, and we have the elements of the set there: Monday, Tuesday, Wednesday, Thursday, and Friday. And I want to make another set which contains whole numbers, actually, and these are the number of hours that she works. So let's just have a set of whole numbers here. I'm going to call this set H, which is a number of hours that she works, and let's just say that these numbers range from 3 to 7. And finally, I want to have a third set, which are number of sweets. Let's call that S. And these numbers range from 4 to 8. Now you see that the objects that are elements of these two sets, H and S, are just whole numbers. But we're not calling the set of whole numbers. It's over a restricted range of the whole numbers. I'm calling this set capital H, which stands for hours, and I'm calling this set capital S, which stands for sweets. And the point I want to make is that there are two different functions here. There is a function or a mapping which for a given element of this set, for a given day, will tell us how many hours Bethany worked on that day. And there is a second function or a second mapping which tells us for a given number of hours how many sweets Bethany had to eat. And let's just do an example here. Let's look at Thursday. Thursday, Bethany works 6 hours. So there's that mapping. Let me call that mapping F. Okay. Let's just do another one. For example, let's look at Monday. Here's that mapping F, maps to 4. And it's the same mapping. We're just going to call it F. The way that we would write this function down in mathematics is the following. We would say that we're going to name a given element of this set capital D, little d, and we're going to name a given element of this set capital H by little h. And we would say that a given element of this set capital H, namely the number of hours per day, can be obtained by applying this mapping F to a given element of the set D. So, for example, you get the value 6 if you apply this mapping F to the day Thursday. Or you get the number 3 if you apply this mapping to the element of D, Friday. And let's just look at this other relationship here between the number of hours, that set, and the number of sweets. So let's look at 4 hours of work, gave 5 sweets. And as I mentioned, the algorithm she has is that she just has a number of sweets equal to the number of hours work plus 1. So there's actually an easy kind of mathematical relationship there. So for example, yes, 6 hours worked would yield 7 sweets. Let's call that mapping G. And so we would have relationships like, well, let me first of all just write it in general. So that's the general mapping between D and H. And let's write a mapping between H and S. So for a given number of hours worked, applying this mapping G to that, we obtain what I will call little s, a given element of this set of values, which is the number of sweets. And so an example was, let's say, 7 equals G of 6. Now we know in fact that we can write down a generic form for this, which is namely that this function little g is just its argument plus 1. So that looks more mathematical, whereas this function here would not have a simple form. There's no perhaps sort of algorithm that takes you from here to here. It's just Bethany's schedule encoded in that mapping. So these are 2 examples of mappings from days to the week onto some whole numbers, which are the number of hours worked. Another mapping from whole numbers onto whole numbers, from a set H to a set S, telling us how many sweets that she rewards herself with for a given number of hours worked. We could also ask, let's say you didn't know that she sort of had an algorithm. You might just be observing how many sweets that she eats. You would say there seems to be some mapping between the day of the week. I'm going to call that mapping capital F. There seems to be some mapping of the day of the week to the number of sweets that are eaten. And we would call this a composite function. Because really, it's kind of interesting, if you were just observing the sweet wrappers in the bin, so maybe you were, cleaning out her bin every day and you sort of just counted how many sweet wrappers, you would say Bethany always has 5 sweets on a Monday, and she has 8 sweets on a Wednesday, and so on. And you might not know that it's related to the number of hours that she works. So in a sense, a composite function has sort of 2 lives. It has the life from the point of view of the person that is emptying her bin, which is that it's just some fairly random relationship. But it has another life from the point of view of Bethany, who can say, well, the number of sweets I eat is a mapping G of the number of hours I work, H. But H itself is a mapping of the day of the week. And so we see here that the composite function, capital F, is a function of a function. It's the sweet mapping function applied to the hours of worked mapping function. So that's just an example of a composite function and how, in a sense, either is completely valid. This from the bin emptier's point of view and this from Bethany's point of view. That was an example based on discrete values. I now want to do an example based on what we would call sort of continuous values. So I don't want to write down lots of individual elements. Instead, I just want to be a bit more symbolic. It's the weekend and Bethany is climbing a very sort of significant hill. Not quite a mountain, but she's climbing up this hillside. And she's wearing red very sensibly in case she gets in trouble. She can be easily visible and signal for help. And she's got a stick, which is very good. That will help her. And I won't draw it, but she's got a bag on her back too, because she has something. She's kind of a scientist. She has something in her bag that she's using for some measurements. Now, let's think about the height that she is at a given time. Okay, so we have the height of the hill, and time is ticking. So, we can draw a little watch there to indicate time is marching on as Bethany is climbing up this hill. So we can think of a set which is time. I'm going to call it capital T for time. I'm not going to draw any particular elements there, but this is a continuous range of values of the time of Bethany climbing this hillside. And I want to draw another set here, which I'm going to call H. Oh no, I've used H. Let me call it A for altitude. So let's call this A for altitude, just to avoid any confusion. So capital A for altitude, the altitude at which she is at on that hillside. And because she only ever climbs up, we have a one-to-one mapping between the time and the altitude. And let's just draw that. So at some particular time, let's say it was 1 hour and 5 seconds after she left, there's a mapping to a particular altitude that she has reached. Now in her bag, she has an oxygen meter. So she's measuring the concentration of oxygen in the air. And that, as we know, goes down with height because the climbers at very high altitudes have to use oxygen equipment if they're going to survive. I'm going to call that capital O for oxygen. So there'll be a mapping between her altitude and the amount of oxygen available, concentration of oxygen around. So another mapping. And for the sake of variety, let me call this mapping P, and let me call this mapping Q. And for any given time, there is a mapping P to her altitude, and for any given altitude, there's a mapping Q to the oxygen concentration. So formally then, just to give you a sort of a confidence in writing these kinds of functions down, we're labeling our sets with these capital letters. That's sort of a convention, and for a given element of the set, we call that the lowercase letter, little t, for the time. We can think of little a for the altitude, and we can think of little o for the concentration of oxygen. And we would be able to write down these kinds of relationships that we could talk about Bethany's altitude as a function of the time she spent climbing, and we're describing this function or this mapping by P. And we could talk about the concentration of oxygen that Bethany measures as a function of the height that or the altitude that she's at on this big climb. And we're saying that the mapping or the function that takes us from a value of altitude to a value of oxygen is Q. Now, I'm using these very odd letters sort of for a psychological reason here, which is that I'm trying to get the viewers away from this very common language of f of x or g of x or f of y. I think one of the problems that students have with functions is they get very caught up with the symbols, and this becomes a real obstruction to understanding. So I'm just using P and Q here as my mappings. I've got these rather unusual symbols O and A, which maybe folks aren't used to seeing. Perhaps Bethany was, recording using a computer the oxygen concentration, and maybe that recorder just is recording oxygen concentration as a function of time. So there would be a composite function for a given time to a given oxygen content, as recorded by her little piece of equipment that has no knowledge of her altitude. And so from that little digital recorder's point of view, there would be a mapping R that gives you a particular oxygen reading as a function of the time over which that piece of equipment's been turned on. So that's from the piece of equipment's point of view. From Bethany's point of view, she would say, oh, well, the oxygen concentration was a mapping of my altitude, and that in itself was a mapping of my progress in time, my altitude as a function of time. And so again, we see that we have a composite function. You can either think of oxygen as mapping from time, or we can see the oxygen reading as the oxygen as a function of altitude, as a function of time. And that's sort of Bethany's point of view, and that's the recording equipment's point of view, as it were. So that's two examples given there. One with discrete values, Bethany's work schedule on weekdays, and the second using continuous values, Bethany's rather heroic trek up rather a steep and high hill, where she was able to measure a decrease in oxygen concentration, apparently. I hope that you can intuit the sense that there are these, simple mappings from one, what we would call variable to another, i.e. one set of elements to another set of elements. We see here that the type of elements we were dealing with here were whole numbers. The type of elements we were dealing with here are actually real numbers, because they're just continuous time. We might break down time in terms of minutes and seconds, but time is a continuous quantity, and it's a real variable, as is altitude, as is oxygen concentration. So these are mappings or functions that are taking certain real numbers, mapping onto other real numbers. I'm going to end there, and in the second tutorial I'm going to put all of this into a slightly more formal setting and just introduce a little bit of the terminology of functions that are used in mathematics, and then I'm going to just give some examples of the more mathematical type, which I hope then will be clearer for those folks who've watched this introductory tutorial. Right, so thank you very much, and I'll see you then.